Okay, thank you. So I should first of all thank the organisers, as we all do, for the invitation to come and talk to you this afternoon. I should also thank the audience for your persistence and stamina for staying till the bitter end, but that's very much appreciated. So the topic that I thought would be of interest to talk about in the context of this meeting is an application of the sort of concepts of anti-diffusive transport that's a little bit different to many of the talks that we've been hearing during this meeting. What I'm going to talk about has a little bit in common with the problem that Antoine Bernay spoke about just before lunch. But most people, I think, have interpreted anti-diffusion in relation to upscale cascades and turbulence and pattern selection. But there is another aspect that I'd like to draw people's attention to in connection with understanding how the circulation of planetary atmospheres actually work. And that's this phenomenon which I refer to as super rotation. So this is work that's been ongoing. I mean, I've had an interest in this problem for very many years, going back to the time when I used to work with Raymond Hyde, who was one of the early pioneers of many problems. But he certainly introduced aspects of this problem in an area that has some interesting history that I'll be happy to tell you about over a pint sometime if anybody's interested. So I'm going to have to run it by. Right. Seems the device here is not working.
Is it plugged in?
No, it's not plugged in. That's why. Okay. Right.
Yeah, it's okay. Okay.
Right, now let's try. Yes, there we go. Okay, so it arises from this empirical observation that we see that most planetary atmospheres in the solar system appear on average to rotate faster than the underlying planet. And that's why we use the term superrotation. I'll say a little bit more about sort of how we know this and what it actually means. But it is nonetheless a kind of intriguing property that we observe in most, but not all, planetary atmospheres, at least within the solar system, where we can actually make serious measurements of them. It turns out that it's probably most insightful to measure the degree of superrotation with respect to the angular momentum that's actually locked up in the atmosphere itself. And you can look at the angular momentum either in terms of its global angular momentum sort of integrated over the whole planet, or looking at sort of extreme values, so the sort of maxima of local angular momentum within the atmosphere. This will turn out to require the behavior of some sort of anti-diffusive mechanism that's involved in the transport of angular momentum in advective and diffusive circulations, and I'll say a little bit about some of the properties of that, and then go on to describe some early efforts, I guess, to try to develop some sort of scaling theory and that will help us to understand more quantitatively why different planets have different degrees of this superrotation.
It's not true for oceans? For oceans, it's not true, superrotation?
It's true locally, yes, but the circulation of the oceans, of course, is kind of coupled to the atmosphere. So if the atmosphere didn't behave in the way it does, then the oceans would probably behave differently. So the oceans are more complicated, and I'd rather not get into that in the present context. So the scaling theory is based on some very simple, essentially parameterizations of the effects of eddies within the atmosphere in transporting angular momentum. But that's pretty unrealistic, so we'll also be looking at, in more detail, at some more realistic information on the wave zonal flow mechanisms that are actually responsible for this anti-diffusive transport. And anticipating the results here, we'll be interested in either local instabilities or actually forced wave-like structures that may be induced within the atmosphere. And we'll apply these particularly to these planetary bodies, Titan and Venus, and you'll see why I picked those bodies as the talk progresses. So, first question first question to ask, which is a fairly general question, is when is angular momentum actually conserved in a fluid? So, for a circulation that is axisymmetric or symmetric about its rotation axis, then we can actually define it's essentially the axial component of angular momentum, and it's convenient to define it with regard to the angular momentum per unit mass, the specific angular momentum, just as the background rotation component to it, and that due to the east-west component of the wind, and then we have this moment arm, where phi is defined to be latitude. So under those circumstances, and if the flow is axisymmetric, so there are no longitudinal pressure gradients that can exert torques, what you're left with is a conservation equation for this axial specific angular momentum, and we allow for the possibility of processes that might break that conservation on the right-hand side. But if we eliminate body torques and friction from the system, and then we just simply have an axisymmetric circulation, then M is going to be materially conserved by any sort of overturning circulation. And the consequence of that is that you would not expect to see this M parameter to exceed the value that it would have in co-rotation, actually at the maximum value of the radius of the system. So in an axisymmetric flow without these non-axisymmetric or eddies or body forces, then essentially that provides a kind of upper limit on the local angular momentum. But pressure torques in the zonal direction and even molecular viscosity is enough, it turns out, to break this conservation. And so this is actually this conservation law is effectively part of what has come to be known as Hyde's theorem, after he discussed this in any great detail in the 1960s. Press the right button this time. So, given these constraints, it suggests a way in which we can actually quantify the superrotation in a dimensionless sense. So we can make use of Hyde's kind of local limit on M, and we define superrotation as the degree to which Hyde's local limit on M is actually exceeded. And so we can define and dimension this local superrotation index as just simply the maximum value of the M that you observe in the atmosphere, minus the bit that's due to the background rotation, and then normalized by essentially the solid body rotation value. And you can see that this essentially looks something like a Rossby number as it's defined there. And the basic idea here is that if we are in a situation where M is perfectly conserved, then we're going to expect this local superrotation index to be essentially mostly negative, with a maximum value of 0, which you might expect to find essentially on the equator. But, whoops. Okay, so in light of this conservation law, we can also say that if M is materially conserved everywhere, then in a closed system that is isolated, if you isolate the atmosphere even from its underlying planet, then you can also argue that the total volume or mass integrated angular momentum throughout the whole atmosphere must also be invariant. So we could also define a dimensionless global measure of superrotation by integrating the excess angular momentum over the solid body value. So we can also get these integral measures. And it's important to distinguish that these are not measuring the same thing. They are distinctive parameters, and you can have one without the other, as we will see. In this case, so if we use the mass-weighted value, for example, which I'll show shortly, then then M naught is the normalizing quantity, is the total integrated mass-weighted angular momentum for an atmosphere that actually has the same density structure, but is in co-rotation with the underlying planet. So again, we would expect S to be 0 for an atmosphere that doesn't exchange angular momentum with other parts of the planet, but other values may be possible if, for example, there's a frictional interaction with the underlying surface. So where do we observe this kind of phenomenon? So starting close to home, we can look at the Earth. So these are actual fields, so showing latitude and height. So up to about an altitude of about 50 kilometers in this case, from reanalysis of observations. And this shows the temperature structure of the atmosphere, the east-west, the zonal wind over this range, averaged over a typical year. And this shows the stream function for the meridional overturning circulation. So we can see the basic structures here. And from the U field here, we can essentially derive the total axial angular momentum of the atmosphere and actually plot time series of these quantities as they are observed. And the basic message here is that we see typical values of the local equatorial superrotation is robustly, on average, significantly negative, whereas the global superrotation integrated over the entire planet is actually weakly positive. But note the magnitudes. The magnitudes are very small in this case, typically on the order of about 1% or so in both cases. And they obviously fluctuate up and down as the circulation evolves during the seasonal cycle. Where else do we observe superrotation? So two other planetary bodies that are worth looking at and contrasting with the Earth. So Titan is the largest satellite of Saturn. It's a planet-sized body. It's something like 40% the radius of the Earth, but rotates relatively slowly. It rotates, in fact, it's tidally locked in its rotation with its orbit around Saturn, with a rotation period of about 16 Earth days. It has a substantial atmosphere, mainly consisting of nitrogen and hydrocarbons, with a surface pressure of nearly 1.5 bars. And it's been measured that it actually exhibits very strong winds, even though it's a very long way away from the sun. And the winds basically increase from the surface all the way up to about 100 meters per second and greater once you get up to altitudes of around about 100 kilometers or so above the surface. And this varies with the seasonal cycle on the timescale of Saturn's year, which is about 30 Earth years. You can see these are other features that are derived from observations. And taking the zonal velocity map, we can compute the angular momentum, and this turns out to be quite large. And in fact, remember with the Earth, we saw a local superrotation on the order of 1% or so. Here you're seeing values of plus 15. So there's 15 times more angular momentum locally than you would get with any part of the atmosphere that were co-rotating with the underlying planet. If you think that's impressive, look at Venus. So Venus is an Earth-sized planet, something like 90% of the radius of the Earth. It's a rocky planet, and it turns out to rotate extremely slowly. It has a rotation period with respect to the background stars of about 240 Earth days. Not only that, it rotates backwards. So in other words, it rotates in the opposite sense to the rotation to its orbital rotation. It has a massive atmosphere, something like 90 bars surface pressure, mainly consisting of carbon dioxide with clouds at around about the 40 to 60 kilometer altitude, thought to be consisting mainly of sulfuric acid droplets. And it's observed to have this very, very strong eastward flow at the cloud tops, again of order 100 meters per second, rising from very weak flow close to the ground, all the way up to, as I say, well over 100 meters per second once you get above the visible cloud tops.
At which latitudes? Everywhere? Uniformly in latitude?
I'm just about to get onto that, thank you. So this...
Excuse me?
Yes.
Well, on latitude, can you go two slides back?
2 slides back.
There.
Yeah.
The features you showed us on Earth seem to be, was it Earth? Yeah, were symmetric about the equator, and this seems to be just north.
Yeah, because this is not an annual average. We haven't actually observed Titan for long enough to be able to get an annual average of the whole. So this is a snapshot within the seasonal cycle. So during the seasonal cycle, the structure of the zonal wind sort of flips backwards and forwards.
Okay.
Yeah, thank you. Okay, so Venus, as I say, this zonal wind is not limited to the equator. In fact, it spans over most of the planet. And so this actually shows some profiles of the zonal wind as a function of latitude at different heights, essentially derived by looking at the planet. So this is an image of Saturn actually taken by the Japanese Akutsuki mission that's still ongoing. And so you can see that the strong 100 meter per second zonal winds persist over a wide section of the planet, and then just decaying towards zero as you head towards the polar regions. If we compute the local and global superrotation indices for this planet, we get some pretty spectacular values. We get for the local superrotation, at the tops of the clouds, we see that the local superrotation index rises to a value of over 50. So you've got something like 3 orders of magnitude or more larger than we see on Earth. And even when you integrate the superrotation index over the whole planet, the global value is also still very large. Don't worry about looking at all the numbers here, but focus your attention on these 2 columns here, which now look at a whole sample of different planets. And we see that the local superrotation index, which is tabulated here with various estimates, range over a huge range. So from Earth and the gas giant planets, you see very, very tiny values, whereas for the slowly rotating planets, Titan and Venus particularly, you see these huge values with superrotation, with local indices that maybe between 10 and 100, and even globally they are well over 1, whereas for Earth and Mars, which are the 2 other planets we can estimate the global indices for, they are typically on the order of just a few %. So how can we account for all of this? And where does anti-diffusion come in? Well, the anti-diffusion ideas come in essentially through a theorem which was developed partly by Raymond Hyde, partly by Victor Starr, another famous name in atmospheric fluid dynamics. So we can take account of, the object is to take account of processes which break angular momentum conservation, which could be molecular viscosity, or they could be due to non-axisymmetric eddies, and we look for constraints on the transport of angular momentum. So if we consider the conservation relation for the axial specific angular momentum in a steady state, then we can essentially write that as equating the advection of angular momentum on the left-hand side equated to the non-conservation terms that we can put on the right-hand side. And if we now take that equation and integrate it over the toroidal annular volume of a ring of fluid that we can enclose by some closed contour in the meridional plane, which I show as C here, and it's convenient to pick as a contour of the angular momentum itself, which presupposes that there exists a local maximum of this angular momentum quantity, which will typically be somewhere close to the equator, which is the point furthest away from the rotation axis. So if we take C to be a contour of constant m, say m0 minus delta, where m0 is the maximum value, and we integrate the left-hand side of this equation, then you can hopefully see where this is headed. We use the divergence theorem to convert the divergence into a surface integral, and it's a surface integral of mu, but of course m is constant over this contour, so we can take m outside the integral, and what we're left with is m0 minus delta times the surface integral of u dot dn, which just by mass conservation has to be 0. So that's the left-hand side, and therefore if we integrate the right-hand side, we must obtain the same result. And if we are able to represent the torque due to eddies or the non-conservation processes as the divergence of a flux, where E is effectively this flux of angular momentum due to eddies, then from the previous result, then we can essentially reduce this to a surface integral of this eddy angular momentum flux that also has to add up to 0. And that basically means that we can only satisfy this if E dot grad m takes either sign somewhere or another, or else E would have to be everywhere parallel to the contours of m. So in general, what this leads to is the conclusion that non-conservative angular momentum fluxes must be able to transfer m up gradient somehow. Not necessarily in all directions, but it has to be able to achieve some up gradient anti-diffusive flux. So just as an aside, I mean, the simplest kind of process that would break the conservation of angular momentum would be just to use a viscous fluid. And it turns out that even ordinary good old molecular viscosity turns out to be enough to break this conservation in a way that gives us something that is anti-diffusive with respect to angular momentum. So if we take a deep spherical shell, for example, the specific angular momentum can be defined in this way, where capital R is the cylindrical radius, if you like, from the rotation axis. The viscous term we can actually write in this very simple terms, where the viscous term essentially acts along the gradient of angular velocity, because basically viscosity is trying to eliminate stress, and the stress is to do with the departure of the flow from solid body rotation. So if we represent the viscous flux in this particular form, we can see how that relates to the gradient of angular momentum itself, and we can see that it's perfectly possible for E to be up gradient for M in the R direction, in this cylindrical radial direction, but not in the direction that's parallel to the rotation axis. Now that's a sort of fairly general result. Atmospheric scientists tend to make a somewhat more approximated version of this, and I'm just indicating this as an aside because it'll be relevant to some of the calculations that we show in a few minutes. So for a shallow spherical shell, meteorologists typically approximate the problem by assuming that the depth of the atmosphere is much less than the radius of the underlying planet. And so in the traditional approximation, we would actually write that m is just equal to omega a cos phi. So we don't take account of variations in the local radius. The radius of the atmosphere is taken to be the same as the radius of the planet, essentially. Now that may seem a fairly innocuous assumption to make. We can still define the viscous flux in a similar parallel way, except that now the angular velocity is the fluid velocity divided by a cos phi rather than r cos phi. And what that basically means is that when you project this flux in the direction of the gradient of the angular momentum, what you find is that this flux can be up gradient in the latitudinal direction, but not in the local vertical. And that's fine over most of the planet, but of course it does give you a little bit of a singularity effect actually on the equator itself, because that's the direct opposite to what normal viscosity would actually really do. So we can move on to try to develop a simple scaling theory for superrotation, and we need several different ingredients in order to build this up. The first thing is that we need to take account of the meridional overturning circulation and the way in which that will transport angular momentum within the atmosphere. So we can assume that friction will act actually on the planetary surface. So we're going to allow for that, and that will turn out to allow us to see some non-trivial global superrotation. But if we keep the internal transport to be purely conservative, then we're not going to see any local superrotation, just due to the meridional overturning circulation by itself. So the classical model that's become very commonly used in the atmospheric sciences world these days is a simple model derived by Isaac Held and Arthur Hu in 1980. So the aim here is to determine the properties and the width of an axisymmetric Hadley circulation. That Hadley circulation is the low latitude thermally direct overturning circulation that is directly driven by the differential heating, the differential absorption of sunlight and the infrared cooling of the atmosphere. So it's we're looking for a steady axisymmetric circulation that's consistent with steady radiative thermal balance, and is also in hydrostatic and gradient wind balance. By gradient wind, I mean it's a combination of either the geostrophic or cyclostrophic centrifugal terms in balance with the horizontal pressure gradient. So the concept is to have essentially a two-layer atmosphere, one which is the upper layer of which is essentially deemed to be inviscid, so we can essentially apply our angular momentum conservation principle in the upper layer, whereas and it's in hydrostatic and gradient wind balance in the way that's described here. And then we have a lower layer which is in contact with the planetary surface, and there the velocity is taken to be zero near the surface due to the presence of a frictional drag. And so we can see the concept of the axisymmetric overturning circulation shown schematically here. And this is deemed to apply over a range in latitude from the equator, taken to be y equals 0, up to a certain maximum latitude, which we denote here by this y sub m. we assume that the meridional velocity is 0 in the extratropical free atmosphere, in other words, outside the Hadley circulation. And then we will assume that the extratropical zonal velocity just follows essentially a uniform angular velocity profile from the edge of the Hadley circulation towards the pole. And this will turn out to also introduce an important parameter, the so-called thermal Rossby number, where delta H is essentially the equator to pole temperature contrast, G acceleration due to gravity, H the depth of the atmosphere, and omega and A we've already introduced. And then within the Hadley circulation, Hadley cell itself, U is determined essentially by angular momentum conservation, assuming that we start with a 0 velocity essentially on the equator itself to prevent us from having any local superrotation. So if you conserve angular momentum in latitude, then you can solve essentially for the variation of U with latitude, and the end result is that you can then essentially solve. You have enough information now essentially to solve for the maximum extent of the Hadley circulation once you've prescribed what the thermal Rossby number is. We can rearrange this, which can be solved numerically. And then there are various sort of asymptotic limits depending upon whether the thermal Rossby number is large or small. So this can be realized in a numerical model for a continuously stratified weakly viscous fluid in which, so we can still keep the notion that we're not going to allow any local superrotation by allowing the viscosity term, the diffusion term, to act in the vertical direction only. So that essentially means that angular momentum flux can only act down gradient in that direction. So Held and Hoos actually did this. They solved the time-dependent 2D axisymmetric equations numerically with a simple heating and cooling, integrating it to a steady state, and these are some typical solutions that you get for the meridional overturning and for the zonal velocity profile. And you can see that basically the vertical velocity can only diffuse m down gradient, hence there's no local maximum of m exceeding omega a squared, and then the rest of the circulation in fact ends up being quite consistent with this very simple schematic semi-analytic model. So once we've got that solution, we can actually then estimate the global superrotation index for axisymmetric circulations by using the solutions that come out of this numerical model and compute the contributions to the global superrotation index for different latitude bands, sort of separating the Hadley circulation part from the extratropical part. And we can see that that's essentially what this leads to, and where the individual terms are described by these integrals. And to cut a long story short, what we get is the following profile for axisymmetric circulations using the Hadley circulation and extratropical profiles that I've just been describing. And so we get this red curve essentially now as a function of this thermal Rossby number. And so what we can see now is that when the thermal Rossby number is very small, we can see that the superrotation index now depends primarily on this thermal Rossby number, and then there are asymptotic limits that you can get for this setup. So for very small values of the thermal Rossby number, essentially geostrophic atmosphere, then you can see that the superrotation index is essentially proportional to R, whereas at very large values of this thermal Rossby number, this sort of Held-2 type of circulation saturates at a constant value at around about 0.4. And it turns out that the observed values turn out to be satisfied quite well by Mars and Earth, the sort of fast rotating planets. But you can see Titan and Venus are way outliers compared to this very, very simple model. So we've taken account of the meridional overturning circulation without any anti-diffusive process. Now, if we add some representation of eddies, as for example an anisotropic eddy viscosity, so in which we allow for a horizontal diffusion coefficient that is much larger than the vertical coefficient. So this is going to allow us now to have upgradient diffusive angular momentum fluxes. And this was an idea that was first put forward by Peter Girash in the 1970s. So his concept was really just to have angular momentum transferred upwards and polewards by this overturning circulation, the eddies and then have eddies transferring angular momentum preferentially equatorwards, parameterized as this anisotropic viscosity. And in his case, he had to ignore the diffusion of heat. So it was effectively a very large Prandtl number assumption. And then there are various scaling arguments that you can use to determine the conditions under which you might expect to see a very large superrotation. But the main thing is you're trying to aim for conditions where this cyclostrophic sort of centrifugal balance with pressure gradient is dominant. And so that was a sort of a simple theoretical argument, and this is a sort of schematic kind of cartoon of what's envisaged. So you have an axisymmetric overturning circulation and upgradient equatorward transfer of angular momentum by the eddies. And this was then extended by Rossop and Williams in the late 1970s when they showed with some numerical simulations that in fact barotropic instability would actually generate eddies that mix vorticity, and vorticity mixing eddies actually have a similar sort of property, at least qualitatively, to the molecular viscosity type of process. So this was then explored numerically with an extension of the Hell-2 simple axisymmetric model on a sphere, in which they then allowed for both horizontal and vertical viscosity, characterized by vertical and horizontal Ekman numbers, as well as this thermal Rossby number parameter. So they explored essentially a three-dimensional parameter space. And what they then found was that, so here are some typical values that you get as a function of these various parameters, a sort of a collage of these things. So by Matsuda and Yamamoto and Yoden and his co-workers in Japan. So if you fix the vertical Ekman number to be pretty small, and then vary the horizontal Ekman number from something which is very small up to something which is very big, you can see that you go all the way from a very tight jet that is confined to the extent of the Hadley circulation, all the way to something where essentially this super-rotating flow extends over almost the entire planet because of the effect of this very strong horizontal upgraded diffusion. And this applies both for relatively small values of R and also for large values applicable to large, to slowly rotating planets. But note that at the large values of R, essentially the Hadley circulation extends over almost the entire planet. So but as far as the endpoint is concerned with this very large horizontal viscosity, you still end up with essentially super-rotating flow over almost the entire planet. If we take that into account, then with you can also show how the super-rotation index will vary according to these various parameters by solving again another algebraic relation. Which I won't go into too many details. You can look at the Yamamoto and Yoden paper and our recent paper in Journal of Atmospheric Sciences if you want more details. But the end result is that the presence of large horizontal viscosity now extends the variation of the global superrotation from small values of R all the way up to large values of R, in which there are different asymptotic dependencies now that go as the square root of R over this intermediate range, going up to the cube root of R at the very largest values of thermal Rossby number. And now we see that now starts to overlap with the actual observed values in Titan and Venus, which at least indicates in principle how the superrotation of these planetary bodies might actually be achieved and explained. So we're sort of getting there, but the only thing, of course, is that eddies don't actually really behave as a viscous diffusion. And so if you actually look at what eddies really do, so you have to look at the diagnostics of fully three-dimensional systems. So these show effectively the effective what are called EP fluxes, which are essentially the fluxes of wave action in the meridional plane for different values of the rotation speed of a planet. And what you find is for Earth-like planets that are dominated by baroclinic instabilities at middle latitudes, then you see that it's the middle latitudes that essentially dominate the transport of angular momentum, and that's mainly pushing angular momentum into the ground, essentially at middle latitudes. Whereas with very slowly rotating planets, the dominant eddies are essentially associated largely with barotropic instabilities, which then transport angular momentum horizontally, and they're transporting angular momentum essentially towards the equator. So we can see that 3D simulations stay very close to this high Held-and-Howe theory, except around the values of between 10 and 100. So this is the blue curve is the three-dimensional simulations, and that also occurs for Earth and Mars. But U is then in a gradient wind balance. But in the case of this model, it didn't seem to be able to quite reach the fully cyclostrophic conditions, unlike Titan or Venus. But on the other hand, some models have shown themselves capable of doing this. So there's a certain amount of model dependence in getting this kind of behaviour. And in particular, looking at the models that are successful in reproducing zonal wind structures that are similar to what's observed on Venus, it turns out that the equatorial Kelvin wave plays an important role. So this is a wave that was mentioned, I think, in Antoine Vanay's talk as well. So Mitchell and Vallis looked at this question in their simple GCM studies, and noted that the equilibrated state was dominated by Rossby and mixed Rossby gravity waves with only weak Kelvin modes in the equilibrated state, even though Kelvin waves played an important role in actually spinning up the flow. And then they identified that this was partly due to an interesting combination of waves that formed a separate instability called the Rossby-Kelvin instability, which is essentially produced by this resonant interaction between a pair of linear equatorial Kelvin waves and equatorial Rossby waves, which could be shifted into resonance by a sheared zonal wind. So if that is the case, then you can actually study the conditions under which this instability occurs. It depends basically on the presence of a reversal of potential vorticity gradients, but also on a Froude number, which is essentially the ratio of the Doppler shifted frequencies of the Rossby and the Kelvin mode. Actually, looking at more realistic simulations of Titan's atmosphere, for example, we can actually analyse how this particular model was able to achieve similar winds to what was actually observed on Titan. And it turns out that the dominant waves do indeed seem to have structures that are highly suggestive of the presence of Kelvin and Rossby waves, and Rossby-Kelvin combination waves as well, as well as some of the other more classical wave structures. Okay, you can see relating to these, this is a sort of phase speed versus latitude plots showing where most of the energy is found. And the relevance of this Rossby-Kelvin instability is kind of confirmed if you actually look at the diagnosed frequencies of the Rossby and Kelvin wave and the corresponding Froude number. So this instability occurs essentially, if this Froude number occurs, it lies between values of 1 and 2. And actually diagnosing within the numerical simulation, it turns out that within Titan's stratosphere, as modelled here, that condition is actually robustly satisfied for most of Titan's year. In the case of Venus's atmosphere, however, then there are other factors as well, and in particular from infrared remote sensing, you can see that in longitude height plots close to the equator on Venus, you can see this pronounced wave number 2 pattern with a phase variation with height. And this is essentially the thermal tide produced by the day-night contrast in heating. And this is a very strong feature of Venus's atmosphere, but is essentially absent in Titan's atmosphere. And this turns out to be very important because if you add a diurnal forcing, you're directly forcing a wave centered on the equator that itself can also transport angular momentum quite intensely, and can lead to the direct generation of an equatorial jet. And the strength of this jet essentially scales with the absorbed with the square of the absorbed power. So the stronger you heat it, the stronger the acceleration that's generated. And the most recent measurements of Venus's atmosphere, at least at the cloud level, seem to indicate that this thermal tide is actually playing a very important role on Venus's atmosphere in maintaining this spectacular, very large superrotation. So this observational verification essentially from cloud level velocity measurements, which show the angular momentum flux, well, the momentum fluxes due to the tides and due to the other transient eddies that are not related to the thermal tide, actually act in the opposite sense. So the tides are essentially converging momentum. Remember, it's got to be retrograde momentum for Venus's atmosphere, essentially accelerating the Venus's superrotation in the tropics, whereas the transits are apparently acting in the opposite sense, and they're diverging westward angular momentum. So this is, yeah, okay, yeah, I'll wrap up very shortly. So basically, on Venus, we seem to have something that looks a little bit like this Gearash type of scenario, but in which the thermal tides play a very important role. And in fact, the other eddies seem to play almost the opposite role, almost in a form of negative feedback. So this is the sort of cartoon. So just okay. So I'll switch to my take-home messages. So basically, what I hope I've convinced you is that atmospheric superrotation is a common observation in solar system planets, and probably elsewhere as well. And it does entail upgraded angular momentum transfer, both from the planet to the atmosphere and within the atmosphere itself. They're two sort of separate aspects. And this is all facilitated by the transport that's obtained by the thermally direct meridional overturning circulations. There are various mechanisms that we can identify to accelerate and maintain the superrotation. So there's the transport by the meridional overturning circulation itself, which is upwards and polewards, and then you've got upgraded angular momentum transport by eddies that are generated by a range of instabilities and also possibly by thermal tides as well, particularly relevant to Venus. What I didn't quite have time to sort of tell you much about, but numerical models can capture many of these features, but certainly not all of them. There are issues in the deep Venus atmosphere which are still, I think, not very well understood. And there's clearly a great complexity of multimodal wave interactions that are relevant to accounting quantitatively for what we observe. And this is all hampered by a lack of verifying observations, particularly either in the deep Venus atmosphere or indeed for Titan itself. And there are all sorts of other questions that I could go into, but I think in view of the time, I must let you all get some tea and leave a minute or two for questions.
Great.
So thank you very much.
Patrick.
So, I mean, listening to your litany of 101 inequalities in viscosity components and waves and all, I'm thinking, has there been any kind of more general attack on the problem, something in the spirit, say, of ACA, you know, to answer the question of what structures the eddies should have to get the right properties?
The simple answer to that question is not to my knowledge, I think.
I mean, you know, particularly these games with unequal components of nu and all are crying out for something like that.
Yeah. So there's a challenge to the room. Yeah.
You talked a lot about momentum balance. What about energy balance for Titan? It's a very long way from the sun. What is actually forcing it? I mean, is the Hadley circulation there sufficient to actually drive the whole of it?
Apparently it is. So the diagnostics I showed from the model simulation of Titan was using realistic sort of radiative heating and cooling rates, which I agree are orders of magnitude smaller than you find on Earth. But this is one of the sort of slightly counterintuitive aspects of when you look at planets that are a long way away from the sun, you often see some of the strongest winds, and it seems to be, you know, it's not just the absolute strength of the heating and cooling, but it's how that balances against the dissipation mechanisms, which presumably are correspondingly weaker.
At those sort of speeds, you'd imagine the dissipation would be very substantial. But
You might think so, but it all seems to come out in the wash anyway.
Okay, one last question. Brad.
In thinking about the thermal tides for Venus, it's not the tide with respect to the solid surface, but with the atmosphere, is that right? Because the atmosphere is going around much more quickly than the surface.
The terminology tide probably is a little bit misleading because it suggests that it's to do with the impact of the sun's gravity on and it's not that. It's purely due to the fact that one side of the planet is heated by the sun and the other side isn't, and that's essentially exciting a thermal wave.
But I shouldn't be paying attention to the surface heating. I should be paying about heating of the planet.
In the case of Venus, that's right. Most of the incoming sunlight is actually absorbed within the atmosphere rather than finding its way to the surface. There's relatively little sunlight that actually makes it to the surface.
Okay, with that, let's thank Peter again.